Thank you. So my name is Paul. I work as a Swift developer for a company called Broken Hands. And we do server-side Swift consultancy, mainly using Vapor. If you don't know Vapor, it's a web framework that allows you to use or to make any kind of web application using Swift. And when I first joined Vapor, one of the first projects that I worked on was rewriting Vapor's JWT library to use Swift native code instead of bundling boring SSL C code. This was an improvement in a number of ways, namely that we don't have to build boring SSL anymore, which saves us a lot of build time. We don't have to step into C when debugging. The code is generally more readable, and in general, the package became a better citizen in the Swift ecosystem. Now we're working on a new package that aims to provide utilities for authentication and authorization. One of these utilities is Bcrypt, which is a password hashing algorithm. It's very robust and popular, and it's usually the de facto algorithm that's used for password hashing. Currently, in this library, it's simply bundled as a C dependency, and we are calling into the C code. So during the winter holidays, I decided to give it the same treatment as JWT and write my own Swift implementation of it. Afterwards, I benchmarked it. This was the initial result, and I was pretty happy with it. It was correct, and it was just as fast as C. However, Bcrypt is one of those algorithms that you use in debug mode quite a lot too. Just think each time you're creating a user or you're running an integration test, you're probably hashing a password. So I tried benchmarking it in debug mode too. This was obviously pretty disappointing because hashing a password for 5 seconds is not really acceptable. So this talk chronicles how I got into trying to make my Swift library be as fast as C in debug mode. First of all, let's talk about Bcrypt. What is it and how does it work? Bcrypt, as I said before, is a password hashing function that was designed to protect against dictionary attacks. Dictionary attacks are really just brute force attacks based on a table of common words. And the way that Bcrypt protects against these is by being deliberately slow. So where SHA-256, for example, can hash millions of strings per second, in Bcrypt this number drops to tens or hundreds. This also depends on an input that it takes called work factor or cost. Increasing this increases the hash time exponentially, and this can help scale along with hardware developments. Internally, Bcrypt looks something like this. We can see we have two main phases, the setup phase and the encryption phase. And the hashing phase is actually the one making the hash. And it's really just a 64-round loop of encryption, where each key is different. The setup phase is the one preparing all those keys and is actually the one driving the main complexity of this function. Internally, it's based on a cipher called Blowfish, which was enhanced to take a lot of CPU and memory to slow down the algorithm. And it's essentially just a repeated encryption of an initial constant value, where each output of the encryption is used as input for the next one. This is obviously not parallelizable because it's sequential by nature. And this encryption happens elevated to the cost times. So this happens with a common cost like 12, means that we are already encrypting 4,096 times before even hashing the password. So how can we speed this up? I tried 3 main approaches. The first one was simply just passing an O optimization to my package to tell the compiler to optimize the code in debug mode, just like it would be doing in release mode. This worked pretty well. We are again on par with C. However, it brings a lot of problems with it too, because when the compiler optimizes code, it rearranges code, and sometimes it also removes it. This leads to a general bad debug experience because variables can be shuttered out, breakpoints can't hit, and even possible bugs can be introduced. In a security-focused library like this one, we really do not want to risk playing with fire. Also, if you use unsafe flags in your library like I did, this library cannot be used as a dependency. So even if we wanted to, we couldn't use it. So I had to take a different approach, which was simply diving into the code. Instruments told me that this was the code that was taking most of the time. And this is just the Feistel network that's at the base of the enciphering. This gets run millions of times, and as you can see, it takes a two-dimensional array. This array is being accessed a lot here, and again, this happens about tens of millions of times. And in debug mode, array as subscripts are checked. This means that for each check, we have an if function. We have an if that, if again it happens millions of times, can slow down stuff quite a lot. So the first thing I did was replacing my function to take a normal array instead of a two-dimensional one. And this has already a good or a better performance than before, because we are just accessing the array half of the times. In fact, the time is halved. But we can definitely do better than this, because the subscripts here are still checked. So what I wanted to do was remove this check. And the way to do this in Swift is to use unsafe pointers. I also introduced some unchecked operations here, as you can see, with wrapping operators and the truncating if needed initializer. And this gave us a great time, almost as close as C, with 492 milliseconds to hash a cost12 password. However, if you use unsafe pointers like this in a library and also use the strict memory safety flag that we've been gradually adopting in Vapor 5, your codebase will look something like this, which is quite worrisome, if you ask me. So I wanted to solve this, and this led to my third approach, which was using span. Now, span is a new construct that was introduced recently in Swift that's type safe, and it's essentially a checked view into a contiguous section of memory. It doesn't own the data it represents, which means there's no overhead of copying around data, and is the de facto solution for replacing unsafe usage across code bases. So this should definitely get rid of warnings without having to incur in performance drops, right? I implemented it, replacing the function that we had before to take a span and simply passing in the span using a span accessor of the array and benchmarked it. Something's obviously gone wrong here. It turns out that using span is not that straightforward. I did this, which is essentially accessing the span in a loop. And it turns out that there's a lot of overhead in doing this. So the correct way to use span would be to take a span initially and just pass it around to wherever you need to. This also required me to use mutable span, since I needed to mutate the data in various places too. And the problem with this is that span and mutable span are non-escapable. Passing them around requires extra work compared to normal values, like defining ownership, so whether they're in-out, borrowing, or consuming. In-out basically means you want to mutate the value and then reuse it afterwards. Borrowing is a read-only version of the data, and consuming mutates it without having to use it afterwards. We also want to define lifetime dependencies, which is what this flag is all about. So I updated one of my functions to take a mutable span as in-out, and this required me to use lifetimes, or to define lifetimes of my two parameters. In this case, I'm really just saying that the lifetime dependencies of P and S, which are my mutable span parameters, are tied to the lifetimes of the data that is passed to them. So the idea is that the P and S parameters don't outlive the memory that is passed to them. I also updated my other functions, like the unsafe function, which is the one that uses the F function that we saw before to receive spans. In this case, we can accept them as borrowing, since we are not mutating the data in them. And I also updated to use unchecked subscripts for the reason we saw before. In this case, we don't need to add lifetime accessors, because the compiler can figure it out on its own. And I benchmarked again. We have definitely an improvement from before, where we had 3.5 seconds, now we have 1. Unfortunately, this is my final benchmark. I looked at instruments. I'm sure you can read this. And it told me that the time that was being spent majorly in this function, which is the subscript of the span. So even if you're using unchecked subscripts, this is still taking a considerable amount of time, namely 63%. I'm not sure I can do much about it. I hope that this is gonna improve in time. And I also measured what span looked like in release mode. And as we can see, both our span implementation and our unsafe pointers implementation are mostly the same, and quite a bit faster than what C is doing, which is great. So what did we learn about span? It's great because it solves our unsafety problem. Unfortunately, debug performance is not quite there yet, at least for this package. Usability, in my opinion, can also be a bit improved because having to define lifetimes could be done, I think, from the compiler side instead of doing it manually. And for these reasons, for now, Bcrypt will keep using pointers, and we will live with the 63 unsafety warnings. So yeah, I will leave with a request. I want to know if you, I'm sure I've missed some clever compiler tricks using pointers or tips using span, or even a completely different approach that I haven't considered to shave off some milliseconds. So if you have any experience here, I would love to hear from you. Come and find me afterwards. Thank you.